Okay, so the ratio of the skin depth in copper at 10 kilohertz to that of 100 megahertz is, okay, so let's look at what skin depth actually means. Okay, so if you have a conductor, basically there's going to be material all around it. Okay, the conductor is not hollow inside, right? When you have a copper wire, right? So the skin depth is a measure of the current density. Okay, so basically what's going to happen is the current density at this outer surface, say it's probably something like I. Over here, the current density would fall off to 1 by Eth times I. Okay, so that is basically your skin depth. Okay, it's a measure of the current density, and it is basically the distance from the outer edge to the point at which your current density falls off to 1 by E. Okay, so now let's look at how to calculate the ratio of the skin depth in copper at a particular frequency and the other frequency. Okay, so let's move to the next slide. Okay, so your skin depth delta is given by this formula. So delta is equal to root of rho divided by pi f mu. Rho is your resistivity of the material, f is the frequency, and mu is your permeability. So what is the factor that's given to you? Everything else of coppers remains the same. The only thing that's going to change is your frequency. So your delta 1 divided by delta 2 is equal to, since it's inversely proportional to your frequency, I can write this as square root of f2 divided by f1. So now what was your question? Your question was to calculate the ratio, and they've given your two frequencies. So all that's left is to just substitute them and then do the calculation. So you're going to get about 100. That's option C here. Okay, so I'll move on to the next question. The characteristic impedance of free space for propagation of a plane monochromatic electromagnetic wave is around what? So let's look at what this means. Your characteristic impedance, right? What does that mean? You're looking at the resistance. So basically every material has a certain amount of resistance. You look at air, there's going to be a certain amount of resistance. So what is the characteristic impedance of free space for propagation of plane monochromatic electromagnetic wave? Okay, so it's a standard value. That's what you're going to see. Okay, so what is its value? So they've given you 4 options here, and now you need to calculate it. Okay, so the definition of your characteristic impedance of space, it's denoted by Z naught, and it is a physical constant which relates to the magnitudes of your electric and magnetic fields of electromagnetic radiation which travels through the free space. So you're looking at Z naught, which is equal to the magnitude of your ratio of the magnitudes of your electric and magnetic fields. So this is basically magnetic induction, not exactly magnetic field. Okay, it's B. So the difference between that is going to be, your B is actually written as mu naught H, right? So this is your magnetic induction. This is your magnetic field. So it's a ratio of your electric field, magnitudes of electric field and magnetic induction, where E here is your electric field strength and H is the magnetic field strength. So let's look at this. So here you have E. Okay, how can I write this in terms of your magnetic field? So the way I remember is this. Basically, you have E is equal to CB. Okay, so you know how the alphabets go, right? It goes like A, B, and C. So there's going to be a BC together. So I've got E is equal to BC. That's how I remember the value of your E. Okay, so it's kind of like, I don't know if you find that quite trivial, but yeah, this is how I do to remember stuff. So CB can be written over here, divided by, you have mu naught, and then you have B. So your B and B gets cancelled. Now, how can I write my C? C can be written as 1 divided by root of mu naught epsilon naught. It's the square root of, it's 1 by the square root of your permeability and permittivity of free space. Okay, so that's how I get this value. Okay, just a second. I think I've made a mistake here somewhere. Okay, yeah, so this is supposed to be So this is H. So I can't write this as mu naught B. This is B divided by mu naught. So I get a mu naught C here, okay, on top. Now, what do you do here? Here, since you've got your C naught, you can substitute this C is equal to 1 divided by root of mu naught epsilon naught here. So I substitute that here. What do you get then? You get root of mu naught divided by epsilon naught. Okay, so you can also write it this way. Okay, you can write it in terms of epsilon naught C naught. Okay, these are the different forms that I can tell you about. Okay, these are the different forms of writing it in terms of constants that you already know. So you know permeability of free space, you know your C values, you know your epsilon naught. Okay, so what do? Is you substitute them and you can calculate this out. So you can probably check this, check if it works. So you'll have to remember what is your permeability of free space, permittivity of free space, and speed of light. Okay, so you can try this out, work it out, and let me know if you get this answer, 376.47 ohms. So I'd probably ask you in the next session if you got that, or you could probably message me and tell me you've got that, or if you haven't got it, let me know. Okay, so let's move on. Okay, I'll just look at the options because people wanted me to go a little slower this time compared to the last time. So here, what do you have? You've got your option C. When I calculated, this is what I got, okay? 376.47, that's roughly 377. So that's what you get. Okay, so now let's look at this. An isotropic dielectric offers a refractive index of 1.5. Okay, 1.5 to the propagation of a plane monochromatic electromagnetic wave through it. Its dielectric constant is what? Okay, so these are kind of like manipulating these relations that you have between your refractive index and speed of light, because your speed of light is related to your dielectric constant or your relative permittivity and things like that, right? Not speed of light exactly, speed of any wave. Okay, so let's check out what the answer is. So these are the options that are given to you. Again, I'll read it out again. An isotropic dielectric offers a refractive index of 1.5 to the propagation of a plane monochromatic electromagnetic wave through it. Its dielectric constant is what? Okay, so your refractive index is basically, this is the basic definition of your refractive index. It is the ratio of the speed of light to the speed of light in a particular medium. Okay, so now how do I write my speed of light? It is written as C is equal to 1 divided by root of mu naught epsilon naught, okay, standard constants. And the other one is in that particular medium, mu naught epsilon. Okay, so for a material that is not magnetic permeability is mu naught. Okay, for a material, I think I messed this up, for a material that is not having magnetic permeability, you have a mu naught. Okay, so your mu naught, mu is equal to mu naught. That's what you're saying here. So if you have a material, for this material that your wave is moving in, this value of mu will be mu naught. Okay, now n is equal to root of, what do you get? These two parts get cancelled off, right? So what you get is n is equal to root of epsilon divided by epsilon naught. This is basically called your relative permeability. Okay, and it's usually denoted as epsilon r. Now this term is also called as your dielectric constant. So I can write this as n is equal to root of kappa is another term for it, dielectric constant or relative permeability. And now what I can see is your dielectric constant is basically what? Square of your refractive index. So let me go back to the question. What was given to you? A refractive index of 1.5 was given to you. So when you square it, you end up getting your kappa. Okay. So now let's look at the next question. The reflectance in visible region at normal incidence is, okay. So now this question has a bit of an ambiguity. It's not a very nice question because it doesn't tell you what material it is. Okay. It doesn't tell you what material that is there. So these are the options that are given to you, and I possibly couldn't figure it out. I looked at the options and tried to compare it with the thing that was given. Okay, so here you have a question that is incomplete because you need to specify whether it's a conducting medium or a non-conducting medium. Okay, your wave is propagating in. Whether you're talking about non-conducting medium, it's a dielectric. A dielectric basically means an insulator, right? So let's look at this. So if I'm looking at reflection, I'm going to give you all the different cases that are there, so that it's kind of like a good way to like remember all the formula so that you can apply it to a different question. So here your reflection and refraction at the plane interface of two non-conducting medium or your dielectric media at normal incidence. So you have to be very careful because one form of categorizing it is you have conducting medium, and you have non-conducting medium. Okay. And then you can write this as oblique incidence of your wave or normal incidence of your wave. Okay. So for, I think in the BU syllabus, they've just done this part. They've done just non-conducting medium. They really haven't done conducting medium. Okay, if you want the derivation, it's quite intense. I can give it to you if you ask me for it. Okay, so this is a non-conducting medium. You got an oblique or normal incidence, and conducting medium, you got oblique and normal incidence. What they haven't done in the question is specify what is what. Like they haven't specified what medium it is, but they've specified normal incidence. Okay, so reflection and refraction, the plane interface of two non-conducting or dielectric media at normal incidence, your R, this is your reflectance. Okay, so R is equal to N2 divided by N1 divided by N2 minus N1. So basically you have a plane that is going to be given to you. I think you can recall this from the derivation. This was done in the second semester. So there's going to be a plane that's given to you. There's going to be a material with N2 here. There's going to be a material with refractive index N1 here. And then you can calculate the reflectance if it is at oblique normal incidence. This is the simplest case that you have. Okay. Now let's go on to the refractance or the transmittance. So your T is equal to 4 N1 N2 divided by N1 plus N2 whole squared. Next, we come across the condition at oblique incidence. So the wave is probably going to be hitting like this. Okay, it's going to be hitting at an angle, and then it's going to be refracting at an angle. So the formula that you have for that is you've got θ1 and θ2. I really didn't put the diagram here because then it's going to go a long way. I have to cover a question in like 4 minutes or so. So if you want, I can share these derivations with you. I've done them quite well, I think. So I can share those parts with you if you wish me to. Okay, so R is equal to N2 cos θ1 minus N1 cos θ2 divided by N2 cos θ1 minus N1 cos θ2 whole square. Okay, and now your T is equal to 4 N1 N2 cos θ1 cos θ2 divided by N2 cos θ2 plus N1 cos θ1 whole squared. So the only difference between here and here is basically along with your N2, you've had a cos θ1. Along with your N1, you have a cos θ2. So that's the only difference between these two. So if you know this, you know this. All you have to do is put the cosine of the other angles. Okay, it's not, this one is N2, this one is θ1. So you'd have to be careful about that. Other than that, I think this is pretty okay to remember. Now we come to the part where you have the thing in the question. So just a second, yeah. Okay, so the reflection from a conducting plane normal incidence. Okay, reflection from a conducting plane at normal incidence. So one of the media is going to be something like air. Okay, so what is the refractive index of air? It's basically taken as 1. So if you look at the question, you don't have N1 and N2 and things like that. You only have an N and you have 1. Now, this is basically an interesting thing. So you have your refractive index having both complex and real parts. So based on this, this determines whether your this basically determines the reflection and transmission of your wave. So I remember for one of my papers on graphene visibility, I had to like put a lot of layers, okay, and I had to write coding for it. And then what I realized was there was a function here. I had to like take the function, basically it depended on your wavelength. So your N2 basically depended on a wavelength, and I had to compute it for several layers so that I can look at the transmission and reflection of these waves that are going to hit these layers that I had. So basically the project that I kind of worked on was, you had a couple of layers here, a couple of van der Waals layers, and then the layer would hit, and I want to know how much is going to be coming up here and things like that. So that was an interesting thing that I worked on. Now, coming back to this. Okay, so what do you have here? You have your reflectance here. It's basically the same as the other one, but here you have to square it separately, okay? And this looks similar to the previous one, what you had for your non-conducting media. And what you have here is your imaginary part of your refractive index. So here, if you look back at the question, what you have here is you have n minus 1 whole square. 1 is basically the refractive index of air, plus k square divided by n plus 1 whole square plus k square. So that's going to be option B. Okay, so let's move to the next question. So the path of the charged particle in a region of crossed electric and magnetic fields is it helical? Is it hyperbolic? Is it parabolic? Is it circular? Okay, so this is a question that has all wrong options. Okay, so this is a wrong question. I mean, like the options are wrong, the question is not wrong, but the options are wrong. So let me move on to this. So the trajectory of a particle in a cross magnetic field is basically a cycloid. Now I'm going to give you a homework right now. So I want you to work out this derivation. So this is not something that we worked out before, and it's not there in our syllabus either. So it's something that comes up in the 4th semester when you do your relativistic mechanics. So you can try to do this entire derivation and get back to me. Okay, because if I take time to do this, this is going to like go on forever and ever. So you can do this derivation and get back to me. I'll post the material on Google Drive. Now, what's this ansatz? Okay, so these are like fancy terminologies that they use. Basically, it means I am assuming these equations so that I get to my answer. Okay, so that's what it means. It's called ansatz. Okay, so now what do you have? You basically have a cycloid. You can look at this figure and you can see that it's a cycloid. So in the options, you basically had none of them. You have helical, hyperbolic, parabolic, and circular. The thing that you have to note here is it's not just electric field and magnetic field. They've actually mentioned crossed electric fields over here. So that's something that's really key. Okay, so it's basically crossed electric field. So you have to note that. Okay, so let's move on to the next question. Okay, so if the de Broglie wavelength of a helium atom at 300 Kelvin is 0.7 angstrom, then at 60 Kelvin, what will it be? So this is pretty simple. You know what the de Broglie wavelength is. You know that it is related to the momentum. You know that the momentum is related to your velocity. And you also know that the velocity is related to your temperature, right? So you need to get a relationship between your de Broglie wavelength and a relationship between temperature. How does it vary with temperature? Okay, so let's move to these. 4.9 angstrom, 49 angstrom, 0.49 angstrom, and 0.049 angstrom. So let's calculate this out. So your lambda is equal to h divided by p actually, right? Okay, so you basically have a h by p. P is what? Mass into velocity, so h divided by mv. Now v, this is, these would probably, I mean, you would have probably learned this in thermodynamics, you know, like how the speed is related to the temperature. The speed of your particle is related to the temperature. So your v is equal to root of 3 kt divided by 2, okay? And then what do you get? Since your velocity is proportional to your temperature, your wavelength is inversely proportional to your square root of your temperature. So your velocity is proportional to root of t. Lambda is proportional to 1 by v, which is proportional to 1 divided by root 1 divided by, so this is proportional to t. And what do you have here? So you basically have 1 by root of t. I think I should have written this way. Okay, so lambda is equal to 1 divided by root of t. So you can calculate this out. And yeah, you should be getting this answer. So what do you have here is your velocity is proportional to root of t. Lambda is proportional to 1 by v, which is proportional to 1 by root of t. I made a typo here. Okay, so you'll have to do this. I think this is pretty correct, but I made a mistake here. I forgot to add a fraction. Okay, so here you have a root of 300 divided by 600. You have 1 divided by root of 2. And then you have, this is pretty trivial. You can calculate this out. Okay, so let me move on to the next one. Okay, so the probability current density for an unnormalized wave function, your psi is equal to exponential of ikx. Okay, so these are the values that were given to me for the probability current density. So now one key thing that you have to remember is how do you write psi star, right? So you take the complex conjugate of it. So you basically have exponential of minus I kx. Okay. Now you need to remember or by heart the definition of your probability current density. Okay. So that's what we're going to look at. What the definition of your probability current density is. Okay. So you've got a minus I h cross divided by 2m. You've got a del divergence of this function here. Okay. And this basically is not a vector. So you have a gradient here. Okay, so sometimes people get confused here. People start putting dots here. I've had several teachers of mine tell me that they put dots here and they don't put a dot here and things like that. So one, you're looking at your gradient. Okay, gradient always operates on a scalar. Divergence always operates on a vector. So this is your formula. And how do you do that? You substitute your value here, right? You take the divergence of it. So what is your divergence basically? It's dou by dou x I cap, dou by dou y plus dou by dou y j cap, plus dou by dou z k cap. Okay, so you substitute that and you try to apply it here. So these two components go away because you do not have y or z components in it. So you only take this part of it. Okay, so what do you get? Basically dou by dou of this exponential of ikx, and what you end up getting is an ik exponential of ikx. Okay, so this is what you end up getting. And now what do? You also have another vector thing here, right? So you got a unit vector here. So you got an I hat. So what do you do now? This term is going to be exponential of ikx. Okay, and you've got an ik and you've got a j. So this term, when you calculate, sorry, this is an I cap. Yeah. So this term, when you calculate it, you get an ik exponential of ik into an I cap. Okay, so don't get confused between this and this. Okay, so this is your I cap. This is your imaginary number. Okay. And what do you have here? You have an exponential of ikx with a negative sign because it's a psi star, right? So what you see is these two terms go away and you get an ik I cap. Okay, so this term here is a vector. Okay, so again, you have your divergence. Divergence always acts on a vector. This guy is a scalar, so this gradient always acts on a scalar. Similarly, you can compute this part. Okay, I've just done this term for you. Now you can compute this. Okay, so let's move on. Okay, so I've done this part for you. Okay, I've done, just a second, yeah. Okay, I've done this part for you. And you can try doing this on your own now. So what you see is your exponential terms get cancelled off, and then you have a 0. Okay, so when you subtract this off, you get a 0 because you basically end up getting a constant here. Okay, so these two terms get cancelled. I get a ik here. I get a minus of minus ik, so that gives me a 2ik. Okay, I get a 2ik. Now this does not have any term of x, y, or z. So when you do a dou by dou x or dou by dou y or dou by dou z, this entire term goes off to 0. So you end up getting your current density as 0. So your probability current density is 0. So the key thing that you have to remember is by heart this formula up. Okay. So now let's look back at the options. What did you get? Here you got a 0. So that's option D. Okay, so now one important thing that you can remember is, so whenever you have a real wave function, here you had a complex wave function, so you had to compute this. Whenever you have a real wave function, your current density is going to be 0 because these two terms are going to be cancelling off. Why? Because you have a real wave function, your psi star is going to be a psi. Here also your psi star is going to be a psi, so these two terms are going to cancel off and you're obviously going to get a 0. Also know that the current density is proportional to velocity. So when you did this formula, if you had some term, say x here, your k would have come out, right? So you have a k h cross. Okay, when you have something like this, what is it? It's momentum. So if you don't quite recall how that momentum is, I mean like how it is the momentum. So you've got a h k, right? What is your h? Your h is your h cross is basically h by 2 pi. And what is your k? K is equal to 2 pi by lambda. Okay, so basically what you end up getting is a h by lambda, which is actually the definition of your momentum. Okay, if you look at, if you remember the de Broglie wavelength that you wrote, you ended up getting h by p for it. Okay, so that's actually going to give you your momentum. So let's move on to the next one. This is pretty simple. Okay, a particle of energy E incident on a potential barrier of height V0 can tunnel through it if and only if E is less than V0, E is greater than V0, E is equal to V0, or E is equal to 0. Okay, so you're saying when can I tunnel through it? So if you look at a classical, scenario, so if I need to, so say the height of this wall is h and a person is playing with a ball here, okay, and they want to go put it across to the other side of the wall, they're going to have to be able to cross that height h, right? Now what kind of a situation are you looking at in this case? Okay, when can I tunnel through it? So in quantum mechanics, in certain scenarios, okay, let's just narrow down the same situation. And if I have a wall of height h here, it can tunnel through it, even though I do not have the energy to cross the wall. Okay, so that's what we're talking about here. Okay, so when does tunneling occur? When your energy of your particle is less than V0, it can occur. Okay, so quantum tunneling is a phenomenon in which your particles penetrate a potential barrier with a height greater than the total energy of the particles. So your particle has a energy E, and it can tunnel through even though the barrier's height is, the barrier potential is basically greater than your E. Okay, so your E is less than V0. That is option A, right? Okay. So now a nucleus has two states with energies 1 MeV and 2 MeV. If the lifetime of the lower state is 2 nanoseconds, then the lifetime of the higher state will be. Okay, so now what you need to do is you need to look at a relation between energy and time. Okay, you need to look at a relation between energy and time. So what do you do now? Okay, you basically, these are your options that are given to you. Basically, the one thing that kind of like relates your energy time is the energy time uncertainty. So you have a delta E, delta T is greater than and equal to h bar divided by 2, right? So now using this, you can calculate the value. Not only that, now if you look at this, you can kind of like eliminate the options. So your nucleus has two states with energies, 1 MeV and 2 MeV. So you have a 1 MeV and 2 MeV, right? So if the lifetime of the lower state is 2 nanoseconds, okay, it can never be equal to 10 nanoseconds because the upper state is going to be so much more excited than that. So your lifetime here, the lifetime for this state should always be less than 2 nanoseconds. Okay, so these two options are directly ruled out. So you don't even have to do the calculations if one of your options is going to be greater. Only one of your options is less than this value. Now, since you have these two options remaining, you probably have to calculate it out. Okay, so this question you can rule out options. It's not very, I mean, like, I think you should try ruling out options first, but actually work out the whole problem one shot again. Okay, so let's move on. So your delta t is greater than or equal to h cross by 2. Your delta E is proportional to 1 divided by delta t. And now what can you write? Since it's inversely proportional, you have a delta E1 divided by delta E2 is equal to T2 divided by delta T1. So you have 1 MeV divided by 2 MeV. Okay, that's what was given to you here, right? So your energy levels of the two states, 1 MeV and 2 MeV. So obviously the higher energy state is going to be on top. The lower energy state is going to be at the bottom of your spectrum. Okay, so now what can you write? You can calculate the value of 2. It's pretty simple. Cancel these two out. So you end up getting 1 nanosecond. So now I'll start discussing this. So I'm going to be discussing the maths of it a little bit. So it's going to be a little confusing. Just listen to this a little bit more carefully. Okay, so the vectors of dual spaces are called, okay, KSET vectors, Bra vectors, Dirac vectors, and Poisson vector. Okay, so there's nothing called Poisson vector. I kind of like had to clarify this with a t-shirt of mine. So there's nothing called Poisson vector. I think there's Poisson algebra, but there's nothing like a Poisson vector. Okay, so what are dual vectors? So the dual vectors are your dual vector space is related to a real vector space V. Okay, it's a vector space of linear functions. So it's basically a mapping from one vector space to another vector space. Okay, so if this is a real vector space, this is a function how you write it for real vector spaces. So if V is a real vector space, you're mapping it onto your R. Okay, so R is a real vector space, V is also a real vector space, and you're mapping one from one space to another. Okay, so one of them is called a dual of the other. Okay, now if I write this in terms of complex functions, okay, I can also write this in terms of complex functions. So I basically have F from V, if it is a complex vector space, to about C. Okay, so they usually write C in a very bold math way. So this refers to your complex vector space. So now when you're looking in your KSET and Bra vectors, they usually written in terms of complex vector spaces. Okay, so let's just a second. So now how is a Bra vector a dual vector? Okay, so you know this is how your KSET looks. Okay, and this is how I'm going to be denoting my vector V. Okay, in this vector space, it's complex. Okay, here V wasn't complex in this example, V was real. Now in this is here, V is complex. Okay, and it represents the state of some quantum system. Okay, now a Bra, this is how your Bra looks, and it denotes a linear function. Okay, so it's basically a mapping from one space to the other one. Now if you basically look at your Bra vectors and KSET vectors, so basically if you have a function, say e power I kx as your wave function, okay, you basically have to take your complex conjugate transpose in order to get your Bra function. So this basically would denote your KSET function, and the other one would be your complex conjugate transpose of, just a second, would be the complex conjugate transpose of your particular function. Okay, so if you write these in terms of matrices, it's much more easier to understand. So if I have a matrix, say I and -1, okay, and this is my KSET. Okay, if I take the complex conjugate transpose, I'm going to end up getting a -I and a -1. So I multiplied these two guys. What do I end up getting? I end up getting just a number. Okay. So I end up getting the first row, first column. Okay, that's how you multiply, right? So what do you end up getting? You end up getting a 1, and you end up getting a -1, which end up, so this is a random example that I took, so you end up getting a 0. So that's how you write your, say you have a ket, this is your Bra function, this is your ket. Okay, so that's your Dirac notation. Now it's confusing because initially I thought that it's going to be a Dirac, I have to write this as Dirac vector, because this Bra-ket notation is usually called as Dirac notation. But on second thought, when you're looking at it, they're asking for the dual of the other vector, right? So they're asking for the dual of the vector, then you know that it's going to be, when we go back to the question. So they've asked for the vectors of the dual space. So one space was your V space, okay, which contained something called your ket. And the dual of that space is going to be containing your, sorry, this is not the way you write Bra. This is the way you write your Bra. So that's going to be containing your Bra. And what was that? It is a functional, okay? It's a functional from one space to your complex vector space, okay? It's a linear functional. So now, let's move on to the next one. If there are any questions on this, you can like raise your hand, or there's a raise hand option, I think, so you can raise your hand and I can answer for you. Okay, so now this is your Pauli matrices. These are how your Pauli matrices are denoted, and which of the commutation relation is correct. So they've given you a number of relations. Okay, I'm sure all of you know what a commutator is. Okay, you would have learned it in the first semester. So if you don't know, I'll be explaining it to you anyways and again. So one thing that you need to remember is you need to remember your Pauli matrices, and these are very frequently used. So it's really good to actually memorize them. Okay. So these are how your Pauli matrices are written. Now the way I remember it is this way. Okay. So I know how my identity matrix looks is 1, 0, 0, 1. Okay. So shift the rows of your thing and you end up getting your sigma x. Okay, so you end up getting 0, 1, 1, 0. So shift the rows of the identity matrix to get the sigma x. Now what do you do here? Okay, so that's one way to remember this matrix. Now I remember another thing this way. Okay, so there are several points to remember. Sigma x and sigma, this is supposed to be z, sorry. Okay, sigma x and sigma z do not have complex numbers in them. Okay, only the middle one, sigma y, has complex numbers in them. That is one way to remember it. Now from here to here, how do you go? Okay, so you have a 0, 1, 1, 0. So 0, I, 0. Okay, the first one does not have a minus sign. The second and third one have minus sign. So the second one has a sign on top. The final one, which is similar to the identity matrix, has the sign at the bottom. Okay, so I don't know if this would help you, but this is how I try to remember it. Okay. So now let's look at what a commutator is. Okay, so if I have two operators A and B, AB minus BA is your commutator. Now, if the commutator is equal to 0, that's when you say the two operators commute. Okay, the two operators commute, and there are physical consequences of that. Okay. So now let's look at your sigma x, sigma y. Okay, so sigma x, sigma y is equal to minus sigma y, sigma x. Okay, so this is how it's written, sigma x, sigma y. You put your sigma x here, put your sigma y here, and put it the other way around, multiply it, subtract it, and you end up with 2i, 1, 0, 0, minus 1, and you get a 2i sigma z. Okay, so what I'd suggest you to do is do all the commutator relations, because you'd at least get these Pauli matrices into your head, and you'd also remember this, because these are very frequently asked things. Okay, there's never been a question paper without the Pauli matrices coming up. Okay, So you can try this for sigma y and sigma z, then try this for sigma z and sigma x. Okay, so once you do one, you should automatically know that what you have a sigma x, sigma y here, and then you have a 2i sigma z. So what happens if you have a sigma y, sigma x? Okay, what happens if you have to calculate that? You obviously know it's a minus of 2i sigma z. Okay, so you can try doing different combinations of these. Okay, so this is a question of Fermi's golden rule. Okay, there happens to be two golden rules for this. Okay, you basically have two golden rules, and these are to deal with transition rates. So you have to mug this up basically, and you have to spit it out. That's what they're wanting you to do. Okay, so here, since I know this, I will go up with option A. Okay, so now I'd really like to discuss a little more on this, a little bit of fun stuff, because Fermi never really worked on these golden rules. Okay, it's somebody else who worked on them. It's Dirac who worked on them, and basically, people started calling this as Fermi's golden rule. So I kind of like realized today why it is that. So I'll just kind of like talk to you about it after I kind of tell you what these Fermi's golden rule are. So Fermi golden rule is a formula that describes the transition rate from one energy eigenstate of a quantum system to a group of energy eigenstates in a continuum, okay, due to a weak perturbation. So we've all discussed about perturbation. Every one of you are from, like at least MSc level or past that. So I think the second semester students have discussed about time-independent perturbation theory. Okay, so now the transition rate is effectively independent of time. So as long as your strength of the perturbation is independent of time. So if your potential is independent of time, the transition rate is also independent of time. Now it is proportional to the strength of the coupling between the initial and the final states of the system. Okay, and this can be described by the squares of your matrix elements. So when you're looking at your function here, right, these are basically going to be matrix elements that you're talking about. Okay, so now this was derived by Dirac and was called the Fermi's golden rule. Okay, so this is basically a function p is equal to 2 pi divided by h bar, and the key thing to remember is, one, it is proportional to the strength of the coupling between your initial and final states, and it is also proportional to the density of your states. Okay, now these are useful in constructing laser systems because it involves transitions from one level to the next level, and that's how you get your laser light, right? So now the story behind its name. So basically Paul Dirac, he kind of like wrote down these formulae, and what happened was when Fermi worked with a lot of he was basically dealt in handling your development of the atomic bomb. So he kind of used these golden rules a lot, and what happened was, as a consequence of that, he had dubbed two of these rules as golden rules in his book on which he taught these nuclear physics course to I think the California Institute of Technology. So he basically discussed about these rules, using these rules in order to work with such systems. And okay, so these are basically rules that have to do with electron transition. So when you're looking at that, he kind of like compared it to that of the work that he needed to do in radioactivity, and kind of like used those formulae and applied it to these radioactive decay rates. Okay, so the first formulae, it's for your first order transitions. It's in Fermi's golden, it's called Fermi's golden rule number 1. Okay, he just mentioned these as golden rules in his textbook. Okay, so he's written this nuclear physics textbook, and it's quite old, and I got a copy of it today, and I'd really like to show you this because it was really hard for them to write these Bra and Ket and all these kind of integrals and things like that. So I mean, like I really appreciate how much they've actually, like, the work they put in those olden days, because it's, I mean, like the technology wasn't there much. So he was talking about all these things and writing them down. It must have taken a lot of time to do it. Okay, so it must have taken a lot of time and a lot of dedication. So you know, this is basically how it got called as golden rules. So he basically took somebody else's work and did a, you know, dubbed it as golden rules, and because he dubbed it as golden rules, he got the credit for it. So it's Dirac who actually derived them. Okay, so now let's go to the next question. Now, the behavior of the wave function for a system of two identical fermions under the interchange of particles is. So these are very simple. Okay, you can automatically tell me what it is. Okay, so symmetric, anti-symmetric, vanishing, and singular. Okay, so it's anti-symmetric. So now, when you're looking at Maxwell-Boltzmann statistics, there is no particular okay, so there is no particular symmetry requirement on your wave function when your particles interchange. Okay, so now in the next case, when you have Bose-Einstein statistics, here your wave functions must be symmetric under the interchange of two particles. That means your wave function remains unchanged. Okay, so these basically consist of one coordinate basically consists of spin as well as position coordinates. Okay, so spin and position. So if you interchange any one of them, it should still give you the same wave function. So that's your Bose-Einstein statistics. Okay, it deals with symmetric wave functions. And then when you're looking at the next one, you have Fermi-Dirac statistics, which is going to talk to you about anti-symmetric wave functions. So the wave functions of the two particles interchange here. The signs of the two particles interchange, sorry. Okay, so now let's look at the next question here. Okay, so I think this is something that you have done in BSc a lot. So checking whether the Maxwell thermodynamic relations is correct. And you would always use the mnemonic to write down the table and find this out. Okay, so what I will do for you is I'll do one for you and you can try and do out the rest. Okay, so here these are we basically write down a thermodynamic square to kind of like write down these Maxwell's thermodynamic relations. Okay, so I have learned this so many times and I keep forgetting them all the time. So it's something that, you know, you could write over and over again and try to feed it, because a lot of questions, they just simply ask these questions, although there's like no basis on, you know, like there's no physics behind really mugging up stuff and putting them in your head. So they keep asking these questions, but it's pretty good tool to kind of like, you know, like remember stuff rather than just mugging it up. Okay, so this is a mnemonic called good physicists have studied under very fine teachers. Now, the ones which are bigger in number are the thermodynamic potentials. The ones that are smaller are your pressure, S is your entropy, V is your volume, and T is your temperature. So these things are small. Okay, I've written in small for a reason. These are your state variables, right? And these are your thermodynamic potentials. So there's always this confusion. Somebody told me that this H stands for Helmholtz free energy. No, it's not that. It's entropy. And this is your Gibbs free energy. This is your enthalpy. And this is your Helmholtz free energy. And it's denoted by your F. Okay. So you're going to go and write these in a clockwise manner. Okay. From here to here. Okay. So good physicists have studied under very fine teachers. That's how you're going to go. Okay. So now these are your potentials. These are your state variables. Okay, so you start from here. And now there are two things that you can do with this. One, you can write the Maxwell's thermodynamic relations, or you can write down the thermodynamic potentials. So I'll do one for you now. Okay, so if I have a U here, I kind of like write du. Okay, now I've got S and V to the opposite sides of it. So I write this as, I just write ds. Okay, and I write dv. Okay, now what is opposite to v? There is a p, and there is also a minus sign here, so I write minus p. Okay, what is opposite to s? I write t. Okay, so I write t. Now what do I have? I have a du is equal to t ds minus p dv. Okay, so you can try out the similar things for there's Helmholtz free energy, Gibbs free energy. and your enthalpy. And you can tell me what they are, okay? You can work this out. It's pretty easy to do. Now, another thing that you have is, okay, I basically write this kind of a shape, okay? I write a U, okay? So this is the way my direction is going to be going, okay? So I have this here, okay? I will take this dou S by dou P, okay? At constant temperature, okay? This is the direction that I'm going at constant temperature. And from here, I'm going to go back, okay? From here, I'm going to go back and I'm going to get dou V by dou T at constant P, okay? So these are equal to each other. Now, whenever you have S and P coming on the same side, you put a negative sign. So that's what I'm going to be talking about next, okay? So, okay, so whenever you have an S and P on the same side, you introduce a negative sign to it, okay? So you can check whether you get these different thermodynamic relations and compare it with the options that are given to you there, okay? So I got option B when I did mine, and I compared it, okay? It was option B that was correct. The rest had some kind of issues with them, okay? So it was option B. Okay. Now let's move on to, yeah, this is the last question, I think. Okay, so let's move on to this now. In a grand canonical ensemble, a system A of fixed volume is in contact with a large reservoir B, then, okay? So now there are fancy names called canonical ensemble, microcanonical ensemble, and grand canonical ensemble. So I'm going to simplify that for you, okay? Now, these are the options that are given to you. You need to know whether your system A can exchange only energy with B, system A can exchange only particles with B, A can neither exchange particles nor energy with B, A can exchange both particles and energy with B. Okay, so the first thing that you have is your microcanonical ensemble. So it's an isolated system. There is no exchange of particles, there is no exchange of energy. Okay, so it's isolated system. So your microcanonical ensemble is basically another term for the isolated system. Then you have a canonical ensemble, okay, which describes a system in contact with a heat path. That means there is transfer of energy, but there is no transfer of particles. So that's a canonical ensemble. And then the other one that you have is your grand canonical ensemble. So it describes a system in contact with a heat and a particle bath. So basically it can exchange heat. It can also, that means it can exchange energy and can also exchange the number of particles. Okay. So that is what you have here. So if you look at the options, what are the options that you have? In a grand canonical example, a system A of fixed volume is in contact with a large reservoir B. Then what can you do? You can exchange that, can A and B can exchange both, sorry. A and B can exchange both particles as well as energy. Okay, so that is your grand canonical ensemble. Heat and particle bath. Your heat bath basically means there's exchange of energy.